Now we have the second quintessential problem with equilibrium, and that is given an equilibrium constant and a starting concentration, find the concentrations at equilibrium. Yesterday we went over given an initial concentration and an equilibrium concentration, calculate the concentrations of the other species. There will be similar things we do for each of these. So like before, I might start out writing the equation like this, and it says if the reaction is started with only 0.02 molar A, how much B does that mean we have? We have 0. So we call this our initial condition. What happens after initial change occurs? And then after change, then what happens? And there we see our ice. Right, so some A goes away, some B forms. We don't know how much, so what do we like to call it? We don't know.
X.
The most popular variable letter would be X. And one-to-one stoichiometry, so just X and X. So at equilibrium, we're going to have 0.2 minus X, and that is going to be X. So now what we need is the equilibrium expression, and what's that look like? What goes on top? Close, but not close enough. B, yeah, it's products over reactants. Brackets typically denote molarity. Alright, so far so good. Now we can plug in our values. Case of C equals 8.5. B equals, we take the bottom row of our ice table and plug it in. Then at this point it's just nothing but simple algebra, right? I'm going to multiply both sides by 0.2 minus x. 0.2 minus x times 8.5 equals x. And then I'm going to distribute my 8.5 through, so 0.2 times 8.5, 1.7 minus 8.5x equals x. Alright, now I'm going to add 8.5 to each side, so there's a 1x here. That's going to give me 9.5x equals 1.7. So 1.7 divided by 9.5 is going to equal x. So I'm going to just round to 5 digits. So now we've pretty much answered our question. X is what B equals. I'm going to get lazy and round some more. What does A equal? Concentration of species A.
Isn't it that initial 0.2?
Yeah, so I want to go 0.2 minus 0.178947, whatever. Now, how do we know if we did this correctly?
Plug it in.
Yeah, let's just plug it in. So for B, I have 0.17. I know I rounded. It should come out close enough. So there we go. I think we did it successfully. Any questions about this process?
How do we know that the 8.5023 is correct?
Because it's pretty close to
Okay.
Yeah.
Okay, there it is.
Yeah. Yeah, so we plugged it back in, and that's a reasonable way to check that out. So what did we do? We knew an equilibrium constant, and we knew some starting material, and we were able to calculate equilibrium concentration. And that's kind of the two things, the two major things one can do with equilibrium. Of course, there's a whole lot more. All right, thus far with our example, I didn't write any phases in that one, but phases will be important because so far what we've looked at I would describe as homogeneous equilibrium. The example problem we just did and the one we did yesterday, we had to consider every species in the chemical reaction. Sometimes there's chemical species in the reaction we get to ignore, and that might be this heterogeneous equilibrium. What does that mean? Equilibria in which all the reactants and products are in the same phase are called homogeneous. Now if we have an S written by a chemical species or an L, their concentration is essentially constant. If you have solid gold, it has a molarity, whatever it is, like liquid water has a molarity of 55 moles per liter. And that doesn't change if you have liquid water. So solids, their concentration is a function of their density and molar mass. So you might have learned that most halides are soluble with the exception of lead, mercury, and silver. So here's the lead example. Lead chloride we say is insoluble, but of course we lied. What it means when we say it's insoluble, it has a limited solubility. Some goes into solution. So we can imagine putting this powder into a beaker and adding some water. If we let it sit for a short amount of time, this equilibrium gets established. And it might be a very small amount that goes into solution, but enough does. I would not want to drink the water above it. So what we learned the other day, we would say concentration of lead in brackets, concentration of chloride in brackets. Why is this 2 here?
It's the coefficient.
Because of the 2 here. And we can imagine putting a line and drawing PbCl2 solid down here. But the reason why we don't write this in brackets down here, because it's a fixed concentration of whatever it is. It doesn't change. And we can imagine just moving it up over here and maybe timesing it by some constant. It just gets absorbed. And for a given temperature, the concentration of lead and chloride in a solution that's saturated with solid lead-2 chloride is fixed. And if I add more solid lead-2 chloride, I just have a bigger pile sitting on the bottom of the beaker. We don't get any more of these species in solution. So this is heterogeneous equilibrium. And solids don't show up. We might be tempted to write it in here, but we're never going to have a number. I mean, we could calculate the molarity of solid lead-2 chloride if we want. Here's another famous example. Calcium carbonate, the solid, is in equilibrium with some CO2 forming some CaO. And it says as long as some of these 2 solids remain, the amount of CO2 above this solid will remain constant if we're at equilibrium. So here, this bell jar, perhaps they put some solid in, hooked it up to a vacuum, let it sit, and equilibrium comes established, and you see CO2 gas floating around in there. And here we depicted a large amount of calcium carbonate and a small amount of calcium oxide. And down here we have a large amount of calcium oxide and a large amount of small amount of calcium carbonate. And the pressure of CO2 is the same. These are at the same temperature. So that's what equilibrium constants can tell us. So how do we calculate equilibrium constants? Well, for 2 days we've kind of seen a little bit. We might want to proceed as follows. Tabulate initial and equilibrium concentration. Could be partial pressures for all species. When an initial and equilibrium concentration is given, we calculate a change. And typically we kind of look at it. We could choose any species to be X, but it's typically nicer to use make X be the chemical species that has a coefficient of 1. If you just really like algebra and proving things to yourself, choose the one that's got a 3 in front of it to be X, and then you'll have fractions everywhere else. So number 2, deduce the equilibrium concentrations of all species. So here's an example, very similar to the other 2. A is in equilibrium with 2B. So if I start out with 1/10 of a mole of A is placed into a 1 liter flask. So we're going to keep molarities or partial pressures. It's not going to matter. We want to keep this real simple. We put a 1/10 mole of A into a 1 liter flask, let it sit for a little while, come back, and we measure 0.02 moles of A. Maybe we come back another hour later and we still got 0.02 moles of A. So that tells us we're at equilibrium. Concentrations of the chemical species are no longer changing. So here's what our ice table looks like. Initially, we have whatever we put in the flask, and initially there can't be any B, because it hasn't reacted yet. We allow the reaction to occur at equilibrium, we have 0.02 moles of A. So here's something you don't want to do, which is really tempting. I found myself doing it. You want to write down 0.02 here. And you don't want to do that because then you get the rest filled out and then you don't know what to do. So I tell students, do the bottom row of the ICE table symbolically.
Hence the reason we don't have, it's 0.1 minus x instead of minus 0.02.
Well, it's tempting since you know the concentration of A to just write in the number 0.02. But you need to have this 0.1 minus x equals. So A does equal 0.02. But that tells us what 0.1 minus x equals. So now we get to add 0.01 to each, or subtract 0.01 from each side. And it gives me 0.08 equals negative x. Normally I try and move x first to get it to be positive, but we either say to ourselves, add x to both sides and add 0.08 to each side, or just multiply both sides by -1. The same thing, and then we see that that x is 0.08, and 2x has to be 0.16. What is k? Bet you I do it on the next slide. How boring. 0.16 squared divided by 0.02 equals 1.8. That's real ugly. I guess I didn't calculate it out. But my calculator tells me 1.28. So the other day I said we can approach equilibrium from either side. So here's a reaction. And now we're going to start by adding what we would consider to be product. 0.100 moles of A2D3 is placed into a 1 liter flask. At equilibrium, the mixture contains 0.03 moles of A. What are the concentrations of everything else, and what is the equilibrium constant? So the first thing I like to do is write down the equation, and underneath each species build this thing called the ICE table. Initially, we put in 1/10 of a mole of our A2D3. So at time 0, we know there can't be any D and there can't be any A. And so the interesting thing might be is that we know things have to move to the left. It allows me to put a negative sign, a plus sign, and if I choose this species here to be X, then this comes out easy as 3x and 2x. If you wanted, you could choose D to be X, and then you would have 1/3 of A2D2 and 2/3 X of A. And you could still solve the problem if you like to work with fractions. Raise your hand if you like to work with fractions. Good. Nobody does. So we choose this species to be X, and this we have these whole number coefficients out in front. And as long as we know an equilibrium concentration of one of the species of A here, once again, we want to leave this 2x. We don't want to write 0.03, which I'm always tempted to do until I do it in front of students and lose my train of thought of what happens next. And what happens next is we say 2x equals 0.03. So we're told here at equilibrium, concentration of A equals 0.03 moles in a liter flask. And that tells us, we look up there and we say 2x must equal that. Divide both sides by 2 to get x equals 0.015. And once we know what x is, then we can go 3 times that number. And then we can also come up here, or I guess come over here, and go 0.1 minus 0.085. Then we know the equilibrium concentrations of everything. We can plug that into our equilibrium expression. And so notice here, products, A2D2 is right here. Down below I got concentration of A squared, the concentration of D raised to the cube power.
On the A2D3, where did you get the 0.1? Or is that the flask? Or it's
That's how much we started with.
Oh.
Right, so that's how much we started with, and that's where this came from.
Okay, that makes more sense.
And we know, since we have all this, it had to go that direction. Any other questions? If I knew the constant, and I knew just how much of this I started with, we could solve for what these concentrations are going to be.
But if you have the concentrations and the constant, could you write your balance scale?
Yeah, kind of. Sometimes there's a quiz question that says, write the chemical equation for this expression. And this expression, let me back up to, like if I gave you this and I said, write the chemical equation, you'd say A equilibrium arrows goes to 2B, right? If you know this thing, you can go to an equation. So here might be an interesting thing. This seems much larger than 1, doesn't it? I wish somebody would give me this many dollars, right? If I had $1 million. And we can see 0.085 is larger than these other things. So we know there's more equilibrium favors products. But the weird way it comes out with those things squared, they get smaller. It makes this number blow up a little bit. So I've alluded to this next concept, what we can do with the equilibrium constant, and that is predicting the direction of a reaction. So we have this thing called Q. What is Q?
Or lowercase
I was
q
waiting for
Q.
somebody to mention a Star Trek. This is uppercase Q, and it just stands for the reaction quotient. And it looks just like K, doesn't it? Our equilibrium constant has products over reactants. Here I see products over reactants, and raised to the power of the coefficients found in there. So Q is the equilibrium constant expression when you're not at equilibrium. How do you know you're not at equilibrium? Q doesn't equal K. So Q gives us the same ratio of the equilibrium expression gives, but it's for a system that's not at equilibrium. So perhaps another of the things we do with equilibrium is we plug in some concentrations and we tell two things: whether we're at equilibrium or not, and then which way the reaction is going to move to obtain equilibrium. So here we plug in some numbers and we get a number that is less than K. That means this thing needs to form more products. And we know the reaction is going to move what we'd say in the forward direction, from left to right. If we plug in our numbers and we get our calculator spits out the same number that K is, we know that Q equals K, and that we're at equilibrium. So here, if Q is better, we know that the reaction is going to shift to the left, we like to say. Shift to the left. I want to leave some good stuff for tomorrow.